You can't hear me remotely?
I can hear you.
Oh, Erik can hear me?
Yes.
Yeah, Erik can hear me, so obviously whoever it is has the problems on their end. All right. We still technically have 3 minutes left. We're starting, but anyway, welcome back, everyone. How many people do we have online? Okay, so welcome back, everyone, to the second day. We're going, this hybrid workshop. So today is the first day that we're actually hybrid in a sense, with a remote speaker. So please welcome Erik Schnetter from the Perimeter Institute for Theoretical Physics.
Erik? Oh, that is my cue. Thank you.
That is your cue.
Good morning.
Morning.
I assume you can hear me, and If you cannot hear me, please speak up. I know that I'm here only remotely. That might make it difficult to understand me, and unfortunately, I also can't see your faces. I can't read whether you understand something or don't understand something. So I'm hoping that the more senior people in the room will not be too timid to interrupt me and to relay any questions that I might or might not be hearing in the room. So you mentioned the Perimeter Institute earlier. This is the Perimeter Institute for Theoretical Physics. I am in Canada, southern Canada, and that's a picture I took last Thursday, I think, from a hill across a lake from the building. And each of the individual cubicles here are where the researchers sitting. One of these windows is mine. Now, I would have liked to be there in the room with you, but I also have a family, I have children, and that makes traveling difficult. When I was a student and I didn't have children, I liked to travel and go everywhere. But once you have a family, there are other obligations that kick in. And I'm very glad that these days we have Zoom and other remote ways of interacting. Now, I'm going to describe CarpetX. CarpetX is a driver for the Einstein toolkit. And I do not know what was described yesterday afternoon in the introduction to the Einstein toolkit. So I'm going to cover some basics. And I hope that the organizers will stop me if I repeat something, if I say something boring. And I hope that you also interrupt me if I assume something that hasn't been mentioned yesterday. So a driver for the Einstein toolkit, that is like a scheduler. If you're familiar with CUDA programming, what you write in your code is what happens with the individual grid points, what happens to the physics, and the driver does the other thing. The driver makes sure everything is scheduled on a parallel system, all the multi-threading, the parallelization. It allocates grid functions, writes them to disk, does the checkpointing, and so on and so forth. It's essentially all the computer science infrastructure that Steve described yesterday morning, and we leave then the physics to do. And there is another driver in the Einstein toolkit called Carpet that you're probably going to use. And the new one is CarpetX because X is the new letter. And yes, we called it CarpetX before Twitter got renamed to X. Obviously, X is not the cool letter anymore, but there we are stuck with the name. X stands for exascale. So CarpetX brings three things to the table, and my talk is split into three pieces. And I'm going to explain what CarpetX does and in how far it is or will be an improvement to the future capabilities of the Einstein toolkit. I'd like to ask, who of you has programmed with the Einstein toolkit before? Can you raise your hand? And Steve, can you count and tell me?
About 10 people, I'd say.
Okay. And how many people are in the room? I should have asked.
I don't know, 20, 25.
Okay.
Estimating.
Okay. And online, I see 4 or 5 people who said they have used the Einstein toolkit before. Okay, so about half of that. Very good. So the three pieces of my talk, the first is, oh, and I forgot to say one other thing. Whenever you have a question, please interrupt me. That is just fine. I have no problem. I like things to be more interactive. And if someone wants to interrupt, Steve, please tell them. I might not hear that. So the first feature that CarpetX offers is that it supports exascale computing. Exascale computing means that you can solve really large problems that need a lot of memory and a lot of compute power. And that means the respective codes need to be highly efficient and they need to parallel. They run on many nodes, they use many GPUs, many cores, they use multi-threading, SIMD parallelization, and so on and so forth. And these are features supported by CarpetX so that you, when you program your physics codes, don't have to take care about all of the details. And CarpetX supports CPUs, GPUs, other accelerators, all the modern computing architectures. That's what I'll describe in the first part of the talk. And the second part of the talk, it's going to be a bit more about math, about applied numerical analysis, so to say. And CarpetX supports some modern discretization methods. It definitely supports adaptive mesh refinement. Adaptive mesh refinement means that you have different resolutions in different regions of your domain. For example, if you have a shock front in a neutron star, you can put a higher resolution there. And if you have a bit of a space-time far away where nothing interesting happens, where just some gravitational waves are moving through, then you can reduce the resolution there. It allows for conservative discretization. That means if you have, for example, a certain amount of matter, in our case, in a neutron star, you might have protons and neutrons combined. They're known as baryons, and the baryon number is conserved. They don't just go away. And in your numerical method, you want to ensure that it is also the case that if a baryon is removed from a certain region of your spacetime, it's put back in the other region, that even if you have some numerical inaccuracies, that the total number of baryons stays conserved. And same with momentum and energy conservation. And it also supports constraint preserving discretization. So constraint is something like the divergence of the magnetic field. It should be zero. And if you discretize something, you get a discretization error, you get an approximate solution. And then if you don't pay attention, then the divergence of the magnetic field might just be small, but not exactly zero. And then you get magnetic monopoles and other things that you might not like to have in your simulation. And there exist discretization methods where you can keep the divergence of the magnetic field exactly zero. The magnetic field itself will still be slightly wrong, but it will be wrong in such a way that the divergence remains exactly zero. And the next presentation will be given by Lucas, and he will speak about multi-patch grids, which is another discretization method that has proven very useful for black hole simulations. And finally, in the third part of the talk, I will describe the safety features that we have in CarpetX. If you're programming with the Einstein toolkit, in particular for the first time, then it's like a black box. You write some code, you're not quite sure, read the documentation is unclear, maybe you're a beginning programmer, it's all real life. And CarpetX has safety features, in particular, it catches undefined values. So if you forget to initialize a grid point or something isn't done in the correct order, then it catches these things at runtime instead of just doing something undefined and having errors that are very difficult to find. And that's not just for beginners. This is also for experts, because for experts, the Einstein toolkit is also a black box. And when we introduced these safety models, we caught so many bugs. Just last week, we found a bug in the infrastructure. My fault. Very embarrassing. Very happy that we have these safety features. Okay, I see 2 hands up. I don't know whether these are questions or whether these are still yes votes from earlier. Lucas, Claudia?
This is just the Redmond from before, sorry.
Okay. Well, I assume that's that. Okay, let me begin with the first part of the talk, namely exascale computing. So the Einstein toolkit runs on many architectures. Obviously, when I develop code, I just write it on my laptop, happens to be a MacBook, and the Einstein toolkit runs there just fine. Of course, I can't run any big simulations there because it isn't fast enough and it hasn't enough memory. The Einstein toolkit also runs on workstations and it runs on supercomputers. And the supercomputers might have CPUs or they might have GPUs or other accelerators. So these days, all the fast computers Now, even laptops have so-called heterogeneous architectures. That means the computing power is not just provided by a single CPU, but there are other things as well. I think almost every laptop these days even has a GPU built in. And if you use the GPU, then you get much more compute power than actually the CPUs. It's a bit tedious to do that, but the Einstein Toolkit and CarpetX offer features. That means you can write your code, and then you can choose whether you run it on the CPU or on the GPU without having to rewrite in CUDA or ROCm or any other thing. And that gives you a lot of advantage in the computing power. And programming for a single CPU is easy, but the code will run very slowly. Well, it will run as fast as it did on a computer 20 years ago. So it runs slowly compared to what the hardware can actually offer. And I think I have some numbers here, just showing how important this parallel computing is. If you have running on one CPU core, I assume you see my mouse pointer, and we make some optimistic assumptions that the CPU core runs on, say, 2.5 gigahertz, and there are certain instructions that can do a multiplication and an addition at the same time. It's called a fuse, multiply, add. So let's assume we have these, and modern CPU cores are so-called superscalar architectures. That means they can execute 2 instructions or more instructions at the same time. If you make these as assumptions, then you can run at about 10 gigaflop. That's 10 billion instructions per second. Or I'm using teraflop here. That's 0.01 teraflop per second. That's the straightforward serial code. If you have some Fortran code from 30 years ago, that's probably the speed that you would be getting. Now, if you have a whole workstation, then you have not one core, probably have more core here. I assume 40 cores. Modern workstations can have more than 100. And you can run SIMD code. SIMD code means that the CPU can execute one instruction that acts on multiple values, like a small vector. And then the same computer, which is using the full node, with except of only one core, could run at about 3 teraflop. So that's a factor of 300 difference. You just need to do the parallel programming correctly to get the speed. And if you're using a GPU, here I'm assuming an NVIDIA A100, I don't know whether you're up to date with what is available. That's kind of 2 generations back or so. It's not a really fast one. This GPU provides about 10 teraflop, still a bit faster than a CPU node. And if you use one of the large supercomputers available, then you get 1.2 million teraflop. That's 1.2 exaflop. And they have, I don't know, 40,000 GPUs built in. And the point is that when you write a code, you begin by writing a serial code to make sure it's correct. And afterwards, you want to make sure that it can run efficiently, because if you solve a complicated system, Newton stars the Einstein equations, then you need a lot of computing power. So you want to run in parallel. Even on a workstation, you can easily get a factor of 100 if you do it parallelization properly, and so on. Now, Steve, what do you think? Are people familiar with what SIMD programming or what multi-threading means?
Anybody want clarification on those terms?
Okay, I'm going to switch over to a whiteboard here. This is an adventure to see whether it works, because I'm not getting any feedback from the room. I don't want anybody to be bored
Erik,
or fall asleep.
Erik,
Yes.
There were people who wanted clarification on those terms.
Okay, yes. So I'm going to switch to a whiteboard and I'm going to sketch something. I'm just looking for the whiteboard button here. Is there a whiteboard button? Share, is it a different share button? Man, I tried it yesterday and it was there. Desktop 1, desktop 2. Okay, sorry, I can't find the whiteboard button here on my Zoom. How inconvenient. How could it go away? Okay, maybe if I stop sharing, maybe the whiteboard button will pop up.
if you have multiple screens, sometimes it like goes to a different screen.
Yes. Weird. Maybe I can't in your Zoom meeting.
Brandon, does he have permission to do that? Yes, he does. Okay.
Okay. Well, I found the whiteboard thing. I typed share. I'm going to move it over here. Okay, I can draw something. My controls aren't here, so I can't erase anything. Okay, sorry, it's going to be green and so on. So SIMD. And I'm still looking at you. Yeah, I'm just looking at the whiteboard as well. So on a modern CPU, it turns out that figuring out which instruction to execute is more complicated, takes more time and effort than actually executing an instruction. So the idea that CPU designers have is that when you figure out what to do, you do the same operation multiple times. So for example, if you want to read an element of an array, instead of just reading one element, you might as well read multiple elements from that array. And yeah, if you have an array and read something, so example EA of I, and that, I don't know, then goes into a variable, let's call it X. If you do a SIMD, then you do the same thing 8 times. So instead of reading a single scalar value, you would read 8 values from memory, 1, 4, like that. And so instead of reading one array element, you're reading I plus 1, and so on until I plus 7 at the same time. And the clue is, if these data sit in the cache, then reading one element takes as long as reading 8 elements. So you kind of get 8 times the amount of work essentially for free. A second order effect, it's not quite for free. Or if you want to add something, you write, say, x plus y, and then instead of adding 2 scalar values, you can add 2 of these vectors. So you have another vector here that I want to sketch here with, say, 8 elements. And then when you add them together, then you do 8 additions. Element-wise, these array elements then get added. And again, this happens in about the same time as it would have taken to add just an individual one. So you can make things 8 times faster. I say 8, that's a feature that Intel processors offers. AMD CPUs do that, I think, up to a length of 4. And GPUs have really mastered this. GPUs are really well designed. On a GPU, this length is 32, well, on CUDA CPUs. For historic reasons, they don't call it SIMD, they call it multi-threading. That's a bit of a misnomer because it's actually very different what a CPU calls multi-threading. But the idea is there's one instruction that is executed, and this instruction acts on 32 data elements on a GPU or 8 on a CPU. And this is called SIMD, single instruction, multiple data. And if you want to run an efficient code, and if the code is actually compute bound, it's super important to do that. Of course, if the code is limited by memory bandwidth, but reading data from the global memory, then using SIMD instructions for computation might not help much, because you're doing the computations faster, but the computations aren't what's slowing you down. What slows you down is reading data from in memory. So in that case, what you need to do, you need to get a faster memory, or you need to read less data from memory, maybe compress your data or something. But if you're doing a complicated operation, for example, you have a high order stencil, or you do an equation of state calculation that takes a lot of time, then these SIMD operations are quite important. Let's speed this up. And in CarpetX, we have some features to help the SIMD operations. And for historic reasons, it's different for every CPU, every architecture, and so on. And there's a C++ class that helps you do that. That's all I wanted to say about it, because that's kind of, it's not something that CarpetX offers. It's kind of a secondary thing. It's a nice thing to do. I wanted to mention it. It's out of the way now, but not going to say anything more about that. Okay, now I'm going to switch back to my presentation. See how that goes. Okay, this was, yeah, you complain if you can't see anything, right? So this was about SIMD programming and GPU programming. I don't know whether you're familiar with CUDA programming. Essentially, your CUDA, well, I'll show some example codes later on that show you how to do that and how to program on a large distributed memory system. I'll also mention that later. Now, I mentioned earlier that when you develop a new code, it's important to start with a simple and serial code and make sure it's correct and test it well and write some test cases. The Einstein Toolkit has supports for maintaining and running test cases, and make sure it's correct. And the test cases are there. They're easy to run so that when you make changes to it later, well, you can rerun the test cases and you can check whether the code is still correct afterwards. And then after I've written a simple serial code that is correct and does all the physics that we want, the next step, you would measure the performance. And then you see what is slow and why it's slow. And that's the step that everybody likes to skip, because you see the code, you've written your code, it's your code, and in your mind, you're dead sure you know what is slow. Oh man, you say, I'm squaring that number here. That must be really slow. Let's replace x squared by x times x, or things like that. People all have preconceived notations about why code is slow and which code is slow, and even experts, and you're all wrong. I'm telling you, if you think you know why your code is slow and you haven't measured performance, you will be wrong about that. And after you know why the code is slow and then which part is slow, you can improve the code. For example, you can add more and more parallelism slowly. You can add multi-threading or distributed memory parallelism, improve the loops until the code is fast enough. And sometimes you get stuck. The algorithm that you're using, maybe you can't make it faster. If necessary, you can redesign the algorithm. And if you're stuck, you can consult with an expert. And that is much easier if you already have a working code that's just too slow. It's easier than designing something new. And most people actually like to start with step number 4, that they know what they want to write. And instead of writing a simple piece of code, they would write a complicated parallel piece of code, and it's not fast and it's not correct, and then everybody gets really stuck. So if you want to have fast code, the most important is that you need to measure the performance, starting with a simple serial code. Oh, I already mentioned this here. There are many kinds of parallelism that one has. There's the SIMD parallelism, where you can have multiple operations at the same time. There's multi-threading, also called OpenMP. And multi-threading that is done automatically by CarpetX if you use the Einstein Toolkit. That's quite convenient. There's GPU programming as well. There's CUDA for NVIDIA or ROCm for AMD GPUs. It's also handled by CarpetX for you. And there's distributed computing, MPI, where you run on several nodes at the same time with a fast network in between. That's also handled by CarpetX for you. And that's convenient. That helps you write fast code. You only need to care what happens on an individual grid point or an individual finite element grid cell or something, and the rest is done by the Einstein Toolkit. Okay, that is a brief overview over exascale computing and how to do it with the Einstein Toolkit. Sorry, the timer is confusing. I like to know how much time I have. I was going to show some code example later on. If you have questions like that, I'd be happy to answer the questions. Otherwise, I'll switch over to describing the discretization methods. And if there's time in the end, I show some concrete examples for how to program with the Einstein Toolkit with CarpetX. Sounds good?
Yes.
Okay, very good. Modern discretization methods. So this is a picture I found on the interwebs about adaptive mesh refinement. This is someone simulating a shock front. That's that thing here. And you need a lot of resolution here, but not so much resolution elsewhere. So there's a big coarse grid, dark blue, and you see the grid cells become smaller and smaller and smaller. And even the red ones, you don't even see anymore how fine they are close as you get closer to the shock front. This is essentially adaptive mesh refinement, and this is super important if you want to have a efficient code, because close to a black hole where the curvature is large, you need a high resolution, but the curvature decreases like 1 over r as you go away from the black hole. So far away, you need much less resolution. And we use adaptive mesh refinement to make that happen. So let me repeat the features that CarpetX offers. There is adaptive mesh refinement. I'm going to describe that later. There are multi-patch methods that will soon be available. It's going to be presented by Lucas in the next lecture. And then there are conservative discretization methods and constraint preserving discretizations that people use for hydrodynamics and for magnetic fields. And I also mentioned higher order time integration method because many of you will want to solve multiphysics problems because of the Einstein equations and hydrodynamics and maybe electrodynamics and maybe neutrino transport, and you need to couple all these systems. And the method of lines is a nice way to couple these, where you get a higher order coupling. It's not a first order, but the coupled system could also be fourth order accurate if your system is fourth order accurate. So I'm going to go through adaptive mesh refinement and so on and show some sketches. So this is adaptive mesh refinement, how it looks in Carpet. Oh my God. Okay, I forgot to say one thing important, and I can't believe, Steve, that you didn't stop me. CarpetX uses an infrastructure called AmRex. That slide, I don't know where it went. AmRex is a library developed outside of the Einstein toolkit, and we are using it. And CarpetX uses this library for mesh refinement and parallelization and so on. So we shouldn't take credit for that. I need to add a slide about that later on. Very sorry. So this AmRex, AMR, Adaptive Mesh Refinement for Exascale. This is what it's called. Anyway, this is the infrastructure that we're using. So here there might be a coarse grid, probably 16 squared points here. And there are some places that need refinement. So some 2 finer grids overlaid over the coarse grid, and then 2 even smaller red grids overlaid over the blue grids. And in this hypothetical example, we need the resolution here. I don't know, maybe there's a neutron star here and another neutron star sitting here. I don't know why that would be a rectangle. And one thing you should understand about CarpetX is that internally everything is stored in grids and so-called blocks. It corresponds to 3-dimensional arrays. And wherever this coarse grid here, this covers the whole domain. There is nothing cut out where the finer grids are. The finer grids are overlaid over the coarse grid. So you have one coarse grid and then 2 blue grids that are actually rectangles, and overlaid over these 2 blue grids are the red grids here. And in practice, people use 10 levels of mesh refinement or more to make sure that actually works. And here is a slide about multi-threading. Here I have a different setup where we have a coarse grid, this rectangle, and then 2 fine grids here. And if we were running with 2 threads, then one thread could calculate things in this red region, and the other thread could calculating things in the green region. But what if you have more threads? Hypothetically, if you have 8 threads, we need to split up the work even more, and this is called tiling in the AmRex nomenclature. So we take the red block here and split it into 4. So this is still one array, but one thread works on this blue region, calculates everything for the array elements here for these grid points, another thread here, and so on. So in the end, total amount of work can be split over 8 threads. And you can imagine in 3D, and of course in reality, all these grids are much larger. There's nothing 8 cubed, everything is at least 100 cubed or something in a real simulation. then you can get many threads, keep many threads busy. Are you familiar with finite differencing or finite volume methods?
We talked about ghost zones a couple of times yesterday. I don't think we specifically said anything about finite differencing as such, but we mentioned that there were stencils. That was the reason for that.
Okay, thank you. Okay, so I'm going to repeat ghost zones simply because that is important. Now, let's consider the right square here. This is interior of the grid, and these four regions here, they need to be calculated. Let's say you want to calculate, I don't know, the derivative of some electric potential or something here. To calculate the derivative of the potential, say it's a second derivative, you can look at the neighboring points here, and using these 3 points, you can calculate kind of the second derivative in the x direction. And these 3 points, you can calculate the second derivative in the y direction, and then you know the second derivative of the Laplacian here. And if you want to do it here at the boundary, then you need one more point here. And this point here is called a ghost point, and this ghost point is calculated by interpolating from the coarse grid. My mouse cursor likes to vanish. So on the coarse grid, we have one data point here in that cell here. And using this value and the other coarse values that underlie here, remember earlier I said the coarse grid exists everywhere. It's just the fine grid is overlaid. It doesn't cut out anything. You can use linear interpolation or something else, higher order interpolation to calculate the values here. And then if you want to calculate the derivative here, you can use that ghost point here that the infrastructure has provided for you. That is, if you later have calculated everything in the interior here, then CarpetX can fill in the ghost zones from the values that you already calculated on the coarse grid. And here you see a bit of an overlap. So the fine grids are these square here, they are just touching. And then we extend the fine grids by 1 point. And this point here exists twice. It exists in the interior of the left grid here, and it exists in the ghost zone of the right grid. And there's an operation called a synchronization that takes the value from the interior of the left grid and copies it to a corresponding area element in the ghost zone of the right grid. So whenever you perform a calculation, you would perform the calculation only in the interior of a grid, and then you ask CarpetX to fill in the ghost zones, and CarpetX either copies it from a neighboring grid, if that exists, or it copies it from the next coarser grid via interpolation, if that exists, or if you're at the outer boundary, then CarpetX would apply a boundary condition, I don't know, directly boundary condition or something similar. Okay, right now,
Good. We have a question.
Go ahead.
It appears now with the interior that those grids are all like duplicate values. They're not do anything. Those ghost points there.
So can you hear the question, Erik?
I did not. I would not mind if you answer the question or someone else because you're all expert in that. But if you repeat it, I can sketch something on a whiteboard.
So with the interior boundary between the two squares, those points they've been duplicated. It looks like.
Yes, they have been duplicated. The thing is, the array on the right is one array that exists in memory, and the grid points here are stored in another array. And it is very convenient that when you program something, you have that make it look as if the array is infinitely large. So you just make the array a few points larger so that you can access the grid points that logically belong to the other array. So they have been duplicated in the ghost zones. That's why they are ghost zones, because you never calculate them explicitly. It's just whenever in the other array the values change, you need to tell the infrastructure to copy the point over. They're kind of mirror images. Sometimes they're also called halo points instead of ghost points.
So they don't actually appear in the domain?
No, they are not part of the domain. They are just cached, so to say, to make it more efficient and more convenient to access them. But there's no double cover of the domain. And when you write the result to file and visualize it, you would not visualize the ghost points. That would be weird. So there's no actual double cover. It is just, so the only domain consists of the interior of these squares here. It's just sometimes for convenience, you want to access something that doesn't exist in your array. And then you would have to have if statements and look the value up in a different array. And that would be very inconvenient. So to make it convenient, CarpetX adds these ghost zones. But if you think about it from a strict mathematical point of view, the ghost zones shouldn't exist. It's just a computational convenience.
Yes, but the question is, when you report the data, the both part of the ghost zone that overlaps with another zone is real data you report. Correct?
I did not understand that. Steve, can you repeat?
10 minutes.
You have a giant square on the left, you have a giant square on the right. The parts which overlap that are in the interior of the giant squares are real data that you do report, and they are overlap ghost regions.
Okay.
Let's talk about this later.
I'll talk to Steve later.
Okay. Go ahead, Erik, just proceed.
Okay, very good. Yeah, I kind of thought that ghost zones were complicated, so I'm ready to sketch something on a whiteboard here. Depending on how the other people feel, if they are nodding off and then drinking coffee, I can also move on.
I think you should move on.
Okay, very good. So let's go to the third part of my presentation about safety first. The thing is, let's go back to this picture, why this is necessary. If you have a modern language, C, Fortran, C++, or something, then you can declare that certain values are constant. For example, in Fortran, that would be an intent in variable. In C or C++, you can declare something as const. And then if you modify that, the compiler would output an error. It would say you shouldn't do that. So for example, if you want to calculate the derivative of the potential, and the potential is passed in as an array, and then you accidentally, because you have a programming error, modify that array, modify the electric potential, the compiler would catch it and say that that's a problem, don't do that. But that only works for variables. So sometimes here, for example, there are some regions of an array, some array elements that can be accessed and some that shouldn't. For example, in this calculation here, you should be modifying the interior, but you should not be modifying any ghost zones because the ghost zones are supposed to be set by the infrastructure, and programming languages have no way to help you. So if you make a mistake, if you, for example, accidentally write to the ghost zones and put the wrong value there, or if you forgot to set the interior, but you were supposed to, no one catches that. I mean, the programming language doesn't catch that. And that turned out to be quite a problem in characters in the Einstein toolkit. So, because if you make a mistake, you wouldn't notice. I mean, there's an array, you don't set a certain array element, but it has a value from earlier, maybe from the previous iteration. It's probably close to the right value. Who can tell the difference? So we added a ton of infrastructure to make sure that this is now much safer. So every time you write a function, you schedule a function, you have a function that's called by the Einstein toolkit, for example, to calculate the right-hand side or the derivative of potential or something, you need to declare which variables you're reading and which you want to write to, and also which region of the variable you're reading. Maybe you're reading only interior, maybe you're also accessing the ghost zones, and the infrastructure then knows that, and it can check whether the ghost zones actually have been set. And if you say that you write to the interior and actually forget to write to the interior, CarpetX can also catch that. Before calling your function in debug mode, it's a bit expensive, it fills all the grid point, all the array elements that you're supposed to write to, with a poison value. Just call it poison. It's a special value, maybe not a number or something. And then after your routine is done, it checks whether there is any poison left over or whether you overwrote it. And if there's poison left over, then you forgot to write something that you promised you would write. That's an uninitialized value, and it catches that. And that mechanism helped us catch a really bad bug last week. I'm still embarrassed that I made that error, but I'm super proud that this infrastructure bit actually helped find this problem. And then Steve Brand actually was the one pushing for this for a long time, put a lot of effort into that. So thank you again, Steve. And as I mentioned, const declarations and so on, they work for scalar values, but not for individual array elements. And I highly recommend using that. Okay. In the last few minutes, I want to switch over and show some actual code and how it looks like and how to program that. So let me share, let me share some actual source code. Sorry, the window opened in the wrong position, so I couldn't actually see that. Okay, I'm still screen sharing.
5 minutes.
Yeah, there you go. You should now be seeing a small editor window. And there we have a tool called, a small thing called WaveToy. And well, let me show the schedule first. There is a thing called the right-hand side function. And the right-hand side, that is the function where, given a current state vector, we calculate the right-hand side of the state vector in terms for a time evolution. This describes how the system evolves in time. So this is the schedule declaration. You probably saw that all yesterday. The function is called WaveToy, right-hand side. It is written in C++. Yeah, we pretend it's C. I don't know, this is older than C++. It reads the state vector everywhere, and it writes the right-hand side, just the interior on the right-hand side, and then it synchronizes the right-hand side, which will fill in the boundary and the ghost zones on the right-hand side. And the corresponding source code, if you can read C++, looks like this. So there is this WaveToy right-hand side function that I promised. There's a bit of error checking, making sure we have enough ghost zones. And this function is a bit complicated. It supports both second order and fourth order finite differencing. This is this parameter FD order. So let's concentrate on the second order finite differencing here. That's this part. So this part up here, 4 lines, is a bit of boilerplate code. That just means we want to loop over all the grid points. C++ is a bit of a verbose language, so I don't know why this takes 4 lines. It should be a single line. It means we loop over all the interior grid points. And the actual code that you write, which is this code here, only says what happens to an individual grid point. That is the same programming model you'd also use when you do CUDA programming. So this code can also run on a GPU super efficiently. It just says how to evolve an individual grid point, and then the infrastructure does all the rest. It loops over all the grid points, over all the tiles, over all the blocks, all the adaptive mesh refinement levels, and so on. So standard POW just means we want to use a POW function because C++, that's a special thing. And this is the Laplacian, as I mentioned earlier. P.I is the current grid point. Di of D is a direction, 0, 1, and 2. That means we use the grid point to the left, and the current grid point, and the grid point to the right. U is the value that we look at. You might recognize this as a finite differencing stencil written in a bit of a convoluted way. And we divide by the square of the grid spacing. And then the right-hand side for U is given by rho. This is a particular formulation of the scalar wave equation. And the right-hand side for rho is given by DDU, the thing that we calculated here. And this piece of code here that runs on a CPU, it runs efficiently, multi-threaded. It runs on the largest supercomputers on Frontier with MPI. It runs on GPUs. It runs on NVIDIA GPUs, on AMD GPUs, in principle also on Intel GPUs. and so on and so forth. So this is essentially the way you would write down your code, and you would discretize it, and then you can run it efficiently on many architectures. So it doesn't do the SIMD programming, actually, that I mentioned earlier. Okay. There's a few more things I wanted to say about discretization methods and so on, but the timer tells me that I have only 67 left. So I'm going to stop this here, go back to the slides, and we'll take your questions.
Okay, thank you, Erik. Questions?
Will this run on a laptop with a GPU?
Will this run on a laptop with a GPU?
Everywhere, yes.
Next question.
This is kind of naive, but I was under the impression that Cactus already has adaptive mesh refinement. So what's different with CarpetX?
He was
This is
under the
better.
impression.
This is better adaptive mesh refinement. So Carpet had adaptive mesh refinement, but what Carpet did not have is these things here. Oh, I can't highlight. Oh no, and it moves. Okay, the conservative discretization and the constraint preserving discretization. So in Carpet, all the values need to be sitting on a vertex or in a cell. And that means that a mesh refinement interface in Carpet, it's not possible to exactly conserve things. So for example, the amount of matter that flows out of a fine grid is not exactly the same as the amount of matter that flows into the coarse grid. You lose something there. And that means if you have a neutron star, then it was not possible to put a mesh refinement boundary, say, near the surface of a neutron star or any shock fronts, because it would be too inaccurate. And with CarpetX, that will be possible. So this is one thing. The other thing is the parallelization is more efficient because we are now using this ARMREX library. I forgot to put the ARMREX slide there, which has been written as part of an exascale computing project. So these are the two main differences in terms of mesh refinement. One, discretization methods that allow you conservation, and B, more efficiency. Oh, I forgot, GPU support. That was also not possible in Carpet. That is possible in CarpetX.
Okay, thank you.
Any other questions? Peter?
So now again, the example you showed with that inside the loop application, grid space squares, that would be the same as grid points.
Okay, sorry, I cannot hear.
So,
Steve,
question-
maybe you can pass the microphone around, or you will have to repeat the question later on.
The question is, you had in your loop, you had a dx squared in the denominator. Wouldn't it be more efficient to move that outside the loop or whatever, save that as a constant? Can you hear me, Erik?
Yes, I'm baffled. Yes. Maybe not. Maybe the compiler is smart enough. Okay, this is a wavetoid. This is supposed to be simple to understand, and I don't know why the code looked so complicated with the 4D, dim, and so on. I totally should have written it differently. So this is a simple example code. And I hope the compiler is smart enough and to move that squaring out of the loop, but I did not check, actually. No. Thanks. Yeah, no, good point.
Any other questions?
I see a question online, Jose.
Yes, hi, can you hear me?
Yes, perfectly. Thank you for using Zoom.
Yeah, so I had one question because you mentioned about measuring performance. So is there any way or any tool already included in the Einstein toolkit to measure individual performance of, I don't know, operations or of the file writing,
Yes.
file reading, like?
Yes, so there are two things built in. One is we collect statistics, how long each time step takes and how many grid points there are, because the mesh refinement that changes over time. And then you get statistics, for example, how many, I think the measure is cell updates or grid point updates per second you can do. And that I mean, you can compare that to other codes between computers, and that number should be the same independent of the resolution, because it's kind of how many grid points per second your code can chew through. And the other thing is we have timers built in for every scheduled routine, for every thorn. You see how much time is spent in there. And then you, for example, see, well, in this one, I/O takes 80% of the time because you're writing a lot of data for debugging. Well, there's no point in improving any CPU performance because it's I/O bound. But apart from that, if you want to really know what's happening, there are luckily rather good tools available that are independent of Cactus. You can use them from the outside. And if you use NVIDIA GPUs, you would use a tool called ANSYS, NVIDIA system. And you just, I don't know, there's good documentation for that. And if you're running on CPUs, there's a thing called HPC Toolkit that I recommend that can do a similar thing. And this kind of can take a profile, a small snapshot of the run, kind of you look at one iteration and it tells you how much time is spent in what routine and how much data is moved between CPU and GPU and so on. So there are really good tutorials on HPC Toolkit and NVIDIA systems and other things, often actually offered by HPC computing centers. And you would run these tools on an HPC system or on a workstation, and then you can copy the data back on your laptop and visualize it there and learn a lot from it. These tools are non-trivial to use, but you can learn a lot. They're amazingly good. So I recommend attending a tutorial. I'm sure LSU is also offering tutorials on some of these tools because they have nice supercomputers.
Any other questions? Roland.
So, since CarpetX is all new and everything, can you give any comment on the level of effort that one has to expect if one wants to port over an existing analysis code or something simple to CarpetX, or the full featured evolution code, but simple?
Yeah, that Roland is putting his finger into an open wound, so to say. The thing is, people have been using Carpet in the Einstein toolkit for a long time, and CarpetX, we decided we needed to do many things different for good reasons, but now they are different. And if you have an existing code, it might not run anymore. I showed you how to do the loop with the wave toy, and the way people used to do loops in Carpet is different. So I would say if you have an existing code where you write some kernels using finite difference or something, then you basically have to touch the code and modify it. It's a straightforward way, but for example, the way you run the loops is now this C++ closures, what are they called? Lambdas or something, instead of using C macros to loop over the grid points and so on. So the changes are straightforward, but they are necessary. And if you have some other code, for example, you have an horizon finder or a wave extraction module, then this works, one would hope, almost out of the box with CarpetX. And the people who tested that statement found it's not quite true, unfortunately, but it should be straightforward to do that. I mean, there's always something that goes wrong. So if you have an existing code, moving over to CarpetX is unfortunately a bit of an effort, and we'd be happy to help with that. If you have a particular pain point, Roland, please speak up now. I don't want to mislead anybody here.
No.
Any other questions? Okay, well, let's thank the speaker again, and we have a break. Based on the and it's based on the capybara. And if you want to go on YouTube.